You wake up in the morning, you see a beautiful sky, you listen the twittering of birds and the sound of waterfall. You see a beautiful sunrise and the greenery of entire world. Instantly, a question rises in our mind that how the entire world are formed and who created it. Today in this video, we try to find out the answer of this question. It was about 13.7 billions of years ago, when there is nothing exists, then the entire universe exists in a tiny hot and dense dot called singularity. It's mean each and everything, including Earth, Moon, stars, Milky Way galaxy, and whole universe that is actually too large that you cannot even imagine exist in just a hot and dense dot. The quantum fluctuation happen inside the dot and the dot explode with unimaginable force. And there was a terrible explosion happen that never happened again, and this explosion named the Big Bang mean large and massive explode, and the universe came into existence with the lot of energy that released after the Big Bang. When the universe formed, it is extreme denser and too hot. The temperature of universe after the Big Bang was 10 to the power 32 Kelvin. This is too hot and matter does not exist at this temperature, but it cooled down with the passage of time. And the temperature of universe about 10 billion years ago is 3000 Kelvin. And now the temperature of universe is 2.73 Kelvin or negative 270.42 Celsius. This temperature is called cosmic microwave background radiation, and this is extreme cool temperature. As the temperature fell down, the energy changed into matter and the first element of universe formed. This is because according to famous Einstein equation E is equal to mc square, energy and mass is not destroyed but it can interchange from one form to another form. Here the question come in your mind that how matter formed from energy. Now we will try to find out the answer of this question. Let me clearly to you that initially after the Big Bang, the universe is too hot and denser. During this stage, only neutrinos, quarks, and electrons began to form. But as the universe continued to expand and cool, quarks aggregated to produce protons and neutrons. Within about 3 minutes, the universe cooled enough for protons and neutrons to combine and form the nuclei of hydrogen and other light elements like helium and lithium. It took around 3 lakhs and 8,000 years for the universe to cool down to a temperature when nuclei could capture electrons to form neutral atoms. This made the universe transparent to photons, leading to creation of cosmic microwave background radiation. Over the next several billions of years, the presence of dark matter accelerated the formation of structures of the universe. Dark matter gathered in huge filaments under the effect of gravity, which eventually lead to the formation of stars and galaxies. Here we read that how dark matter play constructive role in evolution of universe. Here this question will come in your mind that what is dark matter? Dark matter is a mysterious component of the universe that does not absorb, emit or reflect light. Its presence is discerned with from its gravitational attraction rather than its luminosity. Here are some key points about dark matter. Dark matter makes up approximately 30% of matter energy. Dark energy makes 70% and ordinary visible matter makes 0.5%. Discovery of dark matter. The existence of dark matter was inferred by Swiss American astronomer Fritz Zwicky in 1933. Zwicky discovered that the mass of stars in Coma cluster of galaxies provide only about 1% of the mass needed to keep galaxies from escaping the cluster gravitational pulls. Evidence of the presence of dark matter. Dark matter is like invisible glue that holds galaxies together. It makes up majority of galaxies' mass. Researchers at the University of Waterloo captured the first composite image of dark matter. This image confirms predictions that galaxies across the universe are tied together through a cosmic web connected dark matter. Remember, dark matter remains one of the greatest mysteries in science, and ongoing research continues to deepen our understanding of this exclusive substance. We keep going on our topic. We discuss now that how stars are formed and how they play a crucial role in the formation of heavy matter and make up the universe bright. About 150 to 200 million years after the Big Bang, the universe temperature and density condition allowed for the gravitational collapse of hydrogen gas cloud. These clouds of gases began to clump together under their own gravity, forming the first stars. The first third generation stars were likely very massive, perhaps hundreds of times more massive than our suns. They were also extremely brighter and hot. They emitting high energy radiation that ionized the surrounding hydrogen gas, ending the cosmic dark age and leading to the fall of free ionization. These first stars play a very crucial role in the evolution of universe. They began the process of nucleosynthesis where new heavier elements were formed in their core. When these stars eventually explode as supernova, they seed the universe with these heavier elements which would later to be incorporated into subsequent generation of stars and planets. Stellar death. A star's fate depends upon its mass. Low mass stars. These stars, like our sun, eventually exhaust their hydrogen fuel. Their core contract while their outer layer expand, forming red giant. Red giants shed their outer layer, creating a planetary nebula. The remaining core become a white dwarf, a dense Earth-sized remnant. High mass stars. These massive stars burn through their fuel more quickly. When their core run out of hydrogen, they undergo a series of nuclear reactions forming heavier elements, and these stars are 10 to 25 solar masses large in diameter. Their core collapse under gravity, leading to a supernova explosion. During the explosion, the outer layer are ejected into space while the core undergoes intense compression. The core contracts rapidly, squeezing protons and electrons together. This pressure arises from the Pauli exclusion principle, which prevents neutrons from occupying the same quantum state. Neutron stars are initially scorching hot with surface temperature exceeding 10 million Kelvin. However, they generate no new heat through fusion. Over the time, they cool down inexorably. A neutron star reaches a surface temperature of about 1 million degree Kelvin when it's about 10,000 or 1 million years old. Even older neutron stars like RxJ 1856.5 remain detectable when an average surface temperature about 4,34,000 Kelvin. Stellar black hole. Stellar black hole emerge from massive stars that exert their nuclear fuel. When these massive stars reach the end of their lives, their core collapses under gravity. The core collapses rapidly, leading to supernova explosion. During this explosion, part of star blast out into space. What remained in a dense core, the stellar black hole. Stellar black holes have a mass about 20 times greater than our sun. Primordial black hole. These are smallest type with the mass of large mountain condensed to the size of a single atom. Supermassive black hole. These giants rise at the center of galaxies and have a mass greater than the combination of 1 million sun. Researchers suggest that every galaxy have one supermassive black hole that forming at the same time the galaxy form. There are so many black holes in the universe. Now we discuss the black hole destruction. Black holes are invisible since not even the light escaping from their intense gravity. Scientists see black holes by observing the matter around them. Now we discuss that how planets like our home planet Earth are formed and why Jupiter are so massive and why the Saturn ring are formed. So let's start. Nebula hypothesis. Around 4.6 billion years ago, our solar system began to form from a solar nebula, a rotating disk of gas and dust around the young star Sun. Planetesimals formed within this disk through accretion, the gradual accumulation of material. The planetesimals were made of ice, rock, and iron. Over time, they grew in size and eventually become the building block for planets. As protoplanets grew, their gravity attracted more material. Some protoplanets remained relatively small and rocky, while others became massive enough to capture significant amount of gas, forming the nebula. The gas giants we see today, like Jupiter and Saturn, formed from this process. Natural satellite, commonly known as moon, formed out of disk of gas and dust surrounded planet during the early stage of our solar system evolution. Natural satellites like our moon are formed in a few different ways. Planetary ring. Planetary ring are captivating features around some planets like Saturn and Uranus. How do they form? Particles that might have otherwise formed a large moon end up creating rings. Gravitational pulls from the nearby planet prevent these particles from collapsing into moons. Instead, they remain in a flattened disk, forming the spectral rings we observe. With this, we end the topic.